Imagine a world where the rules of physics are completely turned upside down, where particles move faster than light, and even travel backward in time. It may sound like science fiction, but what if I told you that such a concept isn't just some far-off fantasy, but a real possibility according to certain interpretations of physics? The particle we're talking about is called the tachyon, a hypothetical particle that moves faster than light and could even challenge our very understanding of the universe. If this concept sounds mind-boggling, it's because it challenges everything we think we know about the cosmos. Today, we're diving into the strange, thought-provoking world of tachyons, a realm where the boundaries of space and time blur and even the most established laws of physics are put to the test. We've all heard that nothing can travel faster than light. It's one of the core principles of Einstein's theory of relativity, a framework that has shaped our understanding of the universe for more than a century. According to relativity, the speed of light in a vacuum is the ultimate speed limit of the cosmos. Nothing, no particle, no force, no information, can exceed this speed. Light travels at an incredible pace, about 300,000 kilometers per second or over 1.08 billion kilometers per hour. So if nothing can go faster than light, how is it possible that there might be particles that can? Here's where tachyons come in. Tachyons are theoretical particles that, according to certain models of physics, could travel faster than light. Unlike the photons that carry light, which always travel at the speed of light, tachyons would always be traveling at superluminal speeds, meaning they would exceed the speed of light by definition. While this might sound like something you'd hear in a sci-fi movie, tachyons have been studied in serious scientific discussions for decades. Their existence may seem unlikely, but the intriguing thing is that some researchers believe that their properties might hold the key to solving some of the most baffling mysteries in physics today, including the enigmatic nature of dark matter. The concept of tachyons was first introduced in the early 1960s by American physicist Gerald Feinberg. He was exploring solutions to the equations of special relativity and discovered that there might be particles that could exceed the speed of light. Feinberg called these particles tachyons after the Greek word tachys, meaning swift or fast. Over the years, tachyons became the subject of much debate and speculation, and while they have not been observed directly, they have continued to intrigue physicists. To understand how tachyons could exist, we need to take a closer look at the theoretical framework behind them. According to the equations of special relativity, particles with mass cannot travel at the speed of light, because as they approach this limit, their energy increases exponentially, and it would require an infinite amount of energy to accelerate them to light speed. However, tachyons are different. These particles, if they exist, are theorized to always move faster than light. Their most unique feature is that, unlike other particles, they have a negative mass squared, which means that they do not behave in the conventional manner that we would expect from regular particles. The negative mass concept is a key element of the tachyon theory. In the context of relativity, the mass of a particle is a measure of its resistance to changes in motion. If a particle has a negative mass squared, it would behave in ways that are radically different from anything we've observed. For one thing, tachyons would lose mass and energy as they gain speed, which is the opposite of what happens with regular particles. In fact, the faster they move, the less energy they would need to continue moving at superluminal speeds. This makes it theoretically possible for tachyons to maintain a constant velocity that exceeds the speed of light without violating the laws of relativity. But why is this significant? The fact that tachyons move faster than light opens up a whole new realm of possibilities in physics. For one, it could imply that particles are not bound by the same rules that govern objects with mass. This would mean that the structure of spacetime, the very fabric of the universe, might be more flexible than we've previously thought. Tachyons could provide a way to explore the limits of space and time, potentially allowing us to travel backward in time, communicate instantaneously over vast distances, or even unlock hidden dimensions of the universe. The very idea of particles moving faster than light challenges our understanding of causality, the fundamental principle that cause precedes effect. In the case of tachyons, these particles could theoretically travel backward in time. This raises the possibility of time loops, paradoxes, and other phenomena that have long been the subject of science fiction. If tachyons can move faster than light, and possibly backward in time, it could mean that the sequence of cause and effect could be reversed or scrambled. The implications for our understanding of the past, present, and future are profound, and it's no wonder that tachyons have sparked such intense interest among physicists and cosmologists. But even though tachyons are a mathematically plausible concept, there are still many obstacles to fully incorporating them into our understanding of physics. One of the main challenges is the fact that these superluminal particles seem to violate some of the fundamental principles of quantum field theory. For example, some experts have pointed out that tachyons would require negative energy states, which are not allowed in conventional physics. Energy, in our current understanding, cannot be negative, and this creates a paradox. If tachyons require negative energy to exist, how can they be physically realized? This question has led some researchers to question whether tachyons are a real phenomenon or just an artifact of the mathematical models used to describe them. Another issue with tachyons is their potential instability. Quantum field theory predicts that tachyons would cause a cascade effect, where the presence of a tachyon would destabilize the surrounding spacetime, potentially leading to the creation of more tachyons. This would create an uncontrollable feedback loop, where superluminal particles would proliferate and destabilize the universe itself. The idea of a universe filled with tachyons raises significant concerns about the stability of the laws of physics as we know them. How could we even begin to integrate such particles into the existing framework of quantum mechanics? Despite these challenges, recent work in theoretical physics has begun to address these issues. A groundbreaking study by physicists at Stockholm University has presented a new approach that could resolve the difficulties associated with tachyons. Led by Jürgen Puss, this team has proposed a radical reinterpretation of the quantum field theory that might allow tachyons to fit into the existing framework. According to their research, the problems that have plagued tachyon models may stem from an overly narrow interpretation of the physical space in which these particles exist. Specifically, the researchers argue that the problem lies in the way the Lorentz group, an essential mathematical tool used in quantum mechanics, is represented within a Hilbert space that is too small. The Hilbert space is a mathematical construct used to describe the set of all possible states of a quantum system. In simple terms, it's the framework in which quantum particles exist and interact. According to Puss and his team, the problem with tachyons arises from the fact that their theoretical properties have been confined to a Hilbert space that doesn't fully account for the unusual behavior of these particles. By expanding the Hilbert space and allowing for additional dimensions and states, the researchers have shown that it's possible to include tachyons in the broader framework of quantum field theory without violating the laws of physics. This new model, while still highly theoretical, has sparked a renewed interest in the possibility of tachyons. By broadening the theoretical space in which tachyons exist, it may be possible to resolve the paradoxes and contradictions that have previously made their existence seem impossible. According to Puss and his team, tachyons could be integrated into the existing laws of physics and might even help us unlock some of the deepest mysteries of the universe. But what about dark matter? Could tachyons be the elusive particles that make up dark matter, the mysterious substance that makes up a large portion of the universe's mass but cannot be directly observed? Dark matter has long been a subject of intense research and speculation. We know it exists because of its gravitational effects on visible matter, but we don't know what it's made of. Tachyons could be a potential candidate for dark matter, according to some recent theories. Dark matter is thought to interact with regular matter through gravity, but not through electromagnetic forces, which makes it invisible to traditional telescopes. This makes it incredibly difficult to detect and study. However, if tachyons exist, they could potentially account for the missing mass observed in galaxies and galaxy clusters. In fact, researchers have found that a universe filled with tachyons could explain not only the observed effects of dark matter but also the accelerating expansion of the universe. Dark energy, the force that is thought to be responsible for this accelerated expansion, could also be related to tachyons. The theoretical tachyon cosmology model suggests that tachyons could have played a crucial role in the early evolution of the universe, slowing down its expansion before eventually causing it to accelerate. To test these theories, physicists have turned to observations of type Ia supernovae, explosions of dying stars that have a consistent brightness. By using these supernovae as standard candles to measure cosmic distances, researchers can track the rate of expansion of the universe. Recent data from these supernovae suggests that the tachyon model could explain both the presence of dark matter and the effects of dark energy. The tachyon model fits the data as well as the current standard model of cosmology, which posits the existence of dark matter and dark energy. While this doesn't necessarily mean that tachyons are the answer to the dark matter puzzle, it does provide a tantalizing new avenue for research. The idea that tachyons could be linked to dark matter raises even more questions. If tachyons exist and make up dark matter, what does this mean for our understanding of the universe? It could completely alter the way we think about the cosmos. Tachyons might not just be a theoretical curiosity but could have profound implications for everything from the structure of spacetime to the future of space exploration. Of course, not everyone is convinced by the tachyon theory. Some researchers, like Kofi Yossi from the Institute of Fundamental Research in Seoul, have expressed skepticism about the validity of the tachyon model. According to Yossi, the proposed theory violates the locality principle, a fundamental concept in quantum mechanics that states that interactions should occur at specific locations in space-time. Yossi argues that the existence of particles with negative mass squared is highly unlikely, and the proposed theory leads to unphysical behavior that makes little sense within the current framework of physics. Despite these criticisms, the tachyon theory remains an exciting area of research. Whether or not tachyons truly exist, their theoretical properties offer a glimpse into a world of physics that is still largely unexplored. As researchers continue to probe the mysteries of the universe, tachyons could play a pivotal role in reshaping our understanding of space, time, and the fundamental nature of reality. While the jury is still out on whether tachyons are real or just a mathematical oddity, their potential implications are simply too intriguing to ignore. So, the next time you look up at the stars and wonder about the nature of the cosmos, remember that the possibility of faster-than-light particles, tachyons, could be the key to unlocking the greatest mysteries of all.